construction isn't boring anymore. It's bold, game-changing, and full of surprises. Across the world, builders are turning impossible ideas into real structures faster, cleaner, and smarter than ever before. Walls rise in hours, tunnels dig themselves, and bridges appear overnight, all through techniques that feel more like magic than machinery. Number 10. The City Digger. Beneath the streets of a busy city, there's a quiet monster at work. A machine as long as a train that slowly eats its way through the ground, leaving a finished tunnel behind it. Engineers call it a tunnel boring machine, but to most people it's easier to think of it as a rolling underground factory. At the very front is a huge round metal face with sharp steel teeth. It spins slowly, cutting into soil and rock. Right behind that face, the machine keeps a gentle, steady pressure on the ground so the surface above never sinks. All the dirt it chews up moves backward on a belt like groceries sliding along a checkout line. But here's the incredible part. As the front digs forward, people and robots inside are already building the tunnel walls. They lift in curved concrete panels shaped like thick pizza slices and lock them together into a perfect circle. Each ring they build is tight and waterproof, sealed by rubber gaskets that sit between the pieces. When one ring is done, the machine actually pushes off that brand new wall to move ahead and start the next one. Real projects have shown just how powerful these machines are. In Seattle, one massive tunnel boring machine nicknamed Bertha dug a road tunnel stretching nearly 9,300 feet beneath downtown. Its cutting face was about 57 feet wide, wider than a 3-lane road, and it built a single, enormous tube, big enough for traffic. All that digging happened while people above still shopped, worked, and drove through the city, barely noticing what was happening below. Across the Atlantic in Britain, giant twin tunnel boring machines have carved deep paths for new high-speed trains. Each one created thousands of perfect concrete rings, transforming loose dirt into smooth, dry tunnels that will stay in use for decades. Those rings are the real secret. They lock together, carry the ground's weight, and keep water out, leaving a clean, solid wall as soon as the machine moves past. Number 9. The Inflatable House. What if you could build a house by blowing up a giant balloon, then hardening it into stone? That is the simple idea behind monolithic airform domes. Crews start with a round foundation ring, bolt on a tough fabric shell, and turn on fans. The shell rises like a bouncy castle and locks in the shape of the future home. Builders call that shell the airform, and it is made from strong fabric with a plastic coating so it holds air and shrugs off weather. It is the mold and the roof in one move. Once the airform is standing, workers step through an airlock and spray soft foam on the inside. The foam sticks to the fabric and makes a warm blanket around the whole shell. While the foam is fresh, they set little hangers that will later carry steel bars. Next comes the muscle. Crews tie in those steel bars and spray a layer of concrete over everything. The foam insulates, the steel takes tension, and the concrete takes the rest. Together they become a single curved shell that is light, strong, and hard to damage. Why go to all this trouble? Because the result is crazy strong and thrifty with energy. A dome has no flat walls to catch the wind and no weak roof edge to peel away, so storms have little to grab. Real dome homes and churches have taken direct hits from major hurricanes and kept their main shells intact even when nearby buildings were shredded. The energy side is just as good. That foam and concrete act like a thermos. The thick shell slows heat going in and out, the round shape has less outside area, and air leaks are tiny. Owners and studies report big cuts in heating and cooling because the building coasts through hot days and cool nights without huge swings. Living inside does not feel like a cave. Builders cut in doors and windows, frame walls where needed, and finish the interior like any other home. Big rooms can be wide open because the curved shell supports itself without posts. Another perk is that a lot of the hard work happens fast and undercover. Weather delays matter less once the airform is up, because crews are working inside the bubble. The airform itself usually stays on the outside as a waterproof layer, and then you can paint or coat it to taste. That is one reason these domes pop up in all kinds of places, from harsh coasts to hot plains. You might wonder about cost. The method saves materials because the dome shape uses less material to enclose the same space. Number 8. The overnight bridge swap. Imagine shutting down a bridge after dark and opening it again before sunrise with a brand new one already in place. That's the magic of the overnight bridge swap. Crews build the new bridge right beside the old one, and when the time comes, they roll or slide it into position, bolt it down, pave the road connections, and hand traffic back, all in one short window. It's the result of careful planning and clever machines built to move massive structures with precision. There are two main ways to pull it off. The first is called the slide-in. Picture giant smooth pads made from a Teflon-like material resting on steel rails coated with slick paste. The new bridge sits on those pads and glides into place inch by inch, pushed forward by hydraulic jacks. The second method uses self-propelled modular transporters, flat robot platforms covered in wheels. These slow-moving vehicles lift the entire bridge like a sturdy coffee table and carry it exactly where it needs to go, all without using a crane. One of the most famous examples happened in Utah. Engineers there replaced a span over Interstate 80 in roughly 3.5 hours. They removed the old bridge and slid in the new one all in the same night. When the sun came up, morning drivers crossed over fresh steel and concrete, unaware that the whole thing had changed while they slept. Those robot transporters are fascinating to watch. Imagine a huge remote-controlled centipede made of steering axles. Every wheel set can turn independently, so the platform can move sideways, spin in place, or follow a curve. Operators guide it with joysticks and laser lines, nudging the bridge into position with pinpoint accuracy. The pace is deliberately slow. Slow means safe, steady and gentle on both the road and the bridge being carried. Why do it this way? Because closing a highway for weeks costs people time and money. Slide-in and transporter moves shrink that pain to a single night or a short weekend. Crews also work in safer, cleaner zones, building most of the new bridge away from live traffic, then doing one well-rehearsed move. Agencies report fewer crashes, less noise, and happier neighbors, and the quality tends to be better when most of the work happens off to the side. There are fun little hacks too. On some slides, crews add dish soap to make the rails extra slick. It is simple, cheap, and it works. Other sites use polished pads with special grease that stays put under pressure. Either way, the point is the same: reduce friction, control the move, and protect the structure. Number 7. The floating tunnel. Imagine a tunnel built the same way you'd launch a ship. On land, inside a dry dock, crews build massive hollow sections shaped like long concrete boxes. Each one is sealed at both ends so it can float. When a section is finished, the dock is flooded. It rises like a barge, and tugboats guide it out to sea. That floating piece is then steered to the exact spot where it will rest on the seabed. Before any piece goes down, a shallow trench is dredged along the seabed. It acts like a long parking slot waiting for each section. When the time comes, the floating tube is positioned above the trench and slowly sunk by filling ballast tanks with water, just like a submarine adjusting its depth. Divers and sensors line up the new section with the one already in place. Between them sits a thick rubber seal. Once the fit is perfect, pumps clear out the water inside, pressure tightens the gasket, and that joint becomes watertight. Finally, sand and rock are placed on top, locking the section firmly in place. Piece by piece, the line grows under the water until both ends meet. One of the clearest examples lies beneath the Pearl River Delta, where Hong Kong, Zhuhai, and Macau are joined by a huge sea crossing. The route combines long bridges, 2 man-made islands, and an underwater tunnel built entirely from immersed sections. The tunnel portion stretches roughly 4 1/10 miles and sits between the islands, so tall ships can pass freely overhead. It's a practical answer for busy shipping lanes that also need a highway running through them. Another milestone sits beneath Istanbul. The Marmaray rail tunnel dips under the Bosphorus, reaching about 197 feet below sea level at its deepest point. The deepest immersed tube rail tunnel when it opened. Crews built each section on land, floated it out, sank it one by one, and linked both ends to bored land tunnels. The largest project of all is now taking shape between Denmark and Germany. The Fehmarnbelt link will stretch about 11 miles, entirely built as an immersed tunnel. A shoreline factory is casting each massive section in sequence. Once finished, every piece will float out, sink into the prepared trench, and lock to its neighbor. When complete, the link will replace long ferry rides with a quick trip by car or train, while ships continue sailing right above. Number 6. Suction bucket foundations. Far below the waves, engineers rely on a special tool to anchor massive wind turbines to the sea floor, a tool that looks a bit like an upside-down steel bucket. They lower it gently, switch on a set of powerful pumps, and start pulling water out from inside. The pressure of the sea pushes harder on the outside, forcing the bucket deeper into the seabed, like pressing a cup into wet sand. That's a suction bucket foundation, sometimes called a vacuum anchor. When sensors show the right depth, the pumps stop. That frame is now solid, stable, and ready to carry a wind turbine. Builders love this approach for 3 reasons. It's quiet, it's quick, and it's reversible. Underwater noise from heavy pounding can disturb sea life, but suction buckets slip in almost silently, and when a turbine reaches the end of its life, the whole foundation can be removed by pumping water back in, breaking the seal, and lifting it out. Germany's Borkum Riffgrund 1 wind farm proved the idea on a full-scale project. Engineers built a complete suction bucket jacket on shore, shipped it out, set it down, and pulled it into the seabed using pumps. The foundation, weighing nearly 2 million pounds, was designed for depths of about 100 to 200 feet. Farther north, Scotland's Aberdeen Bay project set a new speed record. One large suction bucket jacket went from vessel arrival to fully installed in roughly 2 hours and 40 minutes. For offshore work, cutting days off an installation is a game changer. Less vessel time, fewer weather risks, and lower costs. This vacuum anchor concept isn't new. Oil and gas engineers have used suction caissons for decades to anchor deep-water platforms. Offshore wind simply borrowed the same physics and adapted it for fixed turbines. Years of testing in both sand and clay led to formal design rules, so every new project can follow proven steps. Number 5. The room stacker. Building a tower no longer has to mean months of hammering in the open air. Today, entire rooms can roll out of a factory already finished. Walls painted, lights working, bathroom fitted, even the air conditioning tested. Trucks bring these completed rooms to the city, cranes lift them into place, and crews bolt them together like building blocks. It's called a volumetric modular high-rise, a tower made from ready-to-live modules that stack neatly into the skyline. The magic begins long before the first truck leaves the gate. Inside a weatherproof factory, rooms move down an assembly line the way cars do. Every cut is straight, every wire and pipe follows the same route, and each module passes a full inspection before it ships. Rain never stops production, and wind never halts work. When the modules arrive on site, they're wrapped, clean, and ready to stack, so the street stays quieter and the neighbors breathe easier. Watching one of these towers rise feels almost like a dance. A crane operator swings a module off the truck while a ground team guides it into position. It settles onto the frame, bolts lock in, and quick connect fittings link water, power, and air. The next module lands beside it, and within hours a full floor begins to take shape. New York proved how far this idea could go. The Citizen M. Bowery Hotel used factory-made guest rooms built in Poland. Each module sailed across the Atlantic, then was lifted and joined in Manhattan's Lower East Side. The result was a slim, modern hotel that became the city's tallest modular hotel at the time, filled with hundreds of identical, pre-fitted rooms that clicked perfectly around a central core. London raised the bar even higher. In Croydon, 2 towers called 10 Degrees used modules built by Vision Modular Systems for Tide Construction and Grey Star. One stands 44 stories tall, the other 38, together holding more than 500 apartments. When they opened, they were widely known as the tallest modular residential buildings in the world. Across the globe, Hong Kong took the same idea and turned it into a smart housing policy. Next to the Science Park, a project called InnoCell used about 418 modules to form a sleek tower of compact homes for tech workers. Each unit came complete with built-in furniture and systems, all assembled off-site. Number 4. The Brick Sprint. On modern job sites, robots are beginning to share the workload with masons. They don't replace people. They take on the heavy, repetitive parts so crews can focus on the craft. One of the best-known systems is called SAM, short for Semi-Automated Mason. Here's how SAM works. A worker feeds it bricks. The robot arm spreads a thin, even layer of mortar, sets a brick on the line, and smooths the excess before moving to the next spot. A laser guide keeps each course straight, and the computer follows a digital layout of the wall. People still handle corners, door openings, and touch-ups, but the long, straight runs happen fast and consistently. On the New Arts building at the University of Nevada, Sam laid thousands of bricks, while crews focused on detail work, less lifting and fewer long hours under the sun. Speed is what makes it stand out. On the right job, Sam can place several thousand bricks a day with just a small team keeping it stocked and checked. That's far beyond what a traditional crew can manage by hand over a long shift. Then there's the big mover from Australia called Hadrian X, built by FBR. Instead of climbing scaffolds, it sits on a truck base and reaches out with a long mechanical boom. Guided by a digital plan, it cuts blocks when needed and places each one with a slim bead of adhesive instead of heavy mortar. That keeps joints neat and helps the arm move quickly from block to block. FBR says that under good conditions, Hadrian X can place up to about 360 blocks an hour, enough to finish the walls of an average house in a single day. Number 3. The Ground Shaker. On some jobs, the fix for weak ground looks almost too simple. A crane lifts a massive steel weight high into the air and lets it drop. The impact shakes the soil, the loose grains pack tighter, and the ground becomes strong enough to hold real buildings. Crews call it dynamic compaction. It's loud, it's basic, and it works. Here's the rhythm of the job. The crew marks a clean grid on the site, like squares on a chessboard. The pounder goes up, then drops straight down. A loader smooths the surface, the crane rolls to the next square, and the process repeats. That grid pattern is planned ahead so the operator knows exactly where to hit and how many drops each spot will get. The pounder itself is no small tool. On many projects, it weighs somewhere between 26,000 and 88,000 pounds, dropped from heights of roughly 30 to about 100 feet. The weight and the drop height change with each site, but those numbers give a sense of the power involved. You don't tighten the whole depth in one round. The work happens in layers. First come the deep hits, heavier drops spaced wider apart to wake up the lower soil. Next comes a medium pass to fine-tune the middle layers. Finally, there's a lighter ironing pass across the top to even out the surface and prep it for foundations or pavement. Between stages, the crew pauses to let trapped water drain and the soil settle before the next round begins. It's a simple rhythm used around the world. This method shines where the ground isn't dependable. Places like warehouse pads, airport zones, port yards, or old fill that was never compacted properly. Instead of digging out weak material and hauling in new soil, dynamic compaction improves what's already there. It raises the soil's bearing strength, cuts the risk of future sagging, and gets the site ready for heavy loads long before concrete arrives. Depth of improvement depends on the soil type and the energy delivered, but most field guides list about 30 to 50 feet as a common range. Engineers adjust the weight and drop height to reach the target, then confirm the results with on-site density and plate load tests. Number 2. The Box That Burrows. Beneath the noise of a busy road or railway, crews quietly build something that feels almost impossible. A giant concrete box that doesn't just sit still, it moves. When the structure is ready, they push the entire thing sideways through the ground until it slides under the road above. Cars and trains keep moving and a brand new underpass appears as if by magic. The move itself is a mix of muscle and precision. The box rests on slick pads laid over steel guide rails. Behind it, a wall of powerful hydraulic jacks presses slowly, inch by inch, sending the structure forward. At the front edge, crews dig out only the soil the box will replace, keeping the ground firm so the surface above never sags. Because nearly all the work happens inside the pit, there's barely any mess on the street and hardly any need to close traffic. A recent example comes from Britain's new high-speed rail project, known as High Speed 2. Engineers built a massive concrete box beside the A46 Kenilworth bypass. Instead of tearing up the road for months, they pushed the box beneath it and connected it to the highway below the surface. The whole sequence, casting, jacking, reopening, happened in one calm, carefully timed window. Another headline job from the same project happened on the M42 near Birmingham. Over a holiday weekend, crews slid an enormous concrete box into place to form part of a new bridge. At the time, it was called the world's longest box slide. The structure weighed about 14,000 short tons and traveled the length of several football fields, yet it moved like a slow, steady parade across the ground. Across the Atlantic, New York pulled off a similar miracle. The Long Island Railroad used an Italian box jacking system to install a new underpass in just one day. For a city that runs on tight schedules, finishing that kind of job in a single day is pure gold. A few clever tricks make it all work. The pads under the box are coated with special grease to keep friction low. The jacks push in small, careful steps, pausing so teams can check their levels. If the soil ahead feels soft, workers reinforce it before the box reaches that point, keeping the roof above perfectly stable. When the box finally settles into place, crews seal the joints, refill the gaps, and rebuild the surface. Number 1. The two-way build. Picture a city block where a new tower is going up. On most jobs, crews dig a deep hole first, then build the basement, then start climbing into the sky. Top-down flips that idea. Here, builders start the ground-level slab first and use it as a sturdy work deck. Then they dig the basement underneath that deck while the tower above begins rising at the very same time. So the building grows up and down together. How do they keep the sides of the hole from caving in? Before that first slab is poured, crews build thick underground concrete walls around the site. Engineers call them diaphragm walls. Think of them as a strong bathtub in the ground that holds the soil back. Inside that tub, long columns or piles are set so the future floors have solid legs to stand on. Once the ground-level slab cures, it becomes a safe platform for people and machines, and it also braces those walls while crews dig below. Each new basement floor they pour becomes the next brace, so the hole stays calm as it gets deeper. Cities love this method because it saves time, where people feel it most, at street level. You do not have a giant open pit blocking sidewalks for months. Noise and dust drop because much of the work happens undercover. Traffic can keep moving, and neighbors get fewer long closures. On tight downtown sites with old buildings close by, the stiff slabs help limit ground movement, which protects those neighbors. Take a look at London's new Elizabeth Line stations. On cramped sites, the project used top-down station boxes, big underground rooms formed by those deep walls, with the ground-level slab cast early so crews could mine and fit out below while street-level work continued above. Thanks for watching. Now check out the videos popping up on screen for more unbelievable stories.